Okay, so session is now recorded. This is the second seminar of the seminar series on cognitive robotics, organized by QMUL and by the CRISP team. And this is also in the context of the cognitive robotics module offered by QMUL to master students. So this is recorded, and the recordings will be made available also for later views. I see a few people are still joining, but we shall start. And today I'm very happy we have Professor Emre Ugur from Boğaziçi University in Turkey, in Istanbul. And so Emre is, I've been knowing him for quite a while. We initially met at some conferences, robotic conferences, and he is indeed very popular in the robotics community and the cognitive robotics community, and especially because he has been doing several works in robot learning. And the impact that his research has had was not only in the, let's say, in the scientific understanding of how humans and biological systems learn and how this can be applied to robots, but also really in robotic application. How can we use this for a robot to do useful and important things in several environments, including industrial environments, and in fact, he has been participating in several collaborative projects, such as European projects funded by the European Commission, which was really that were really targeting this idea of using robot learning, but then apply it to real-world situations. And so I think his work has been very very relevant on both aspects. And as you know, cognitive robotics is exactly this. So understand more about human and biological intelligence through robot, but also create robots that are more intelligent and can do things that are important for our society. And yeah, so I'm looking forward to the talk Emre will give today, and especially for the students of the cognitive robotics module. I'm sure you will have a chance to connect some of the things that we have been seeing in the lectures to the things that Emre will describe in his presentation. And yeah, without further delays, I leave the virtual floor to Emre.
Okay, thanks a lot. Thanks a lot for inviting me. It's always a pleasure to be in the same venue with Lorenzo, who is also very popular in robotics. So actually about cognitive robotics, I had two options for this talk. One option was to give some bits and pieces from different research topics that we study here without any detail. Or the other option was to go into details of one of these research topics. I chose the second one, and this is a very recent work. Actually, I have been working on this topic since a long time, maybe 10 years. But the material that I am going to present is very recent, and it is currently under review for a journal. So this title is a kind of broad title. So I will try to explain what I mean by symbol grounding in robotics, and then I will talk about a particular way of grounding. So now let's start. Yeah, if you have any questions, I don't know, maybe you can ask me directly or after the talk. So first of all, where is my university? It is in Istanbul, Turkey. So on the right, you can see Istanbul is here. And my university, it's actually English is Bosphorus. There is this canal, that connects Black Sea to the Mediterranean, and then so we are on the side of the canal. So on the right, this is a view from the university. This is the canal, and on the left you see the main nice campus and buildings. So Boğaziçi University, so it is one of the top ranking public universities. Actually, it was founded as the first American college outside America at that time in 1863. Then it was integrated into Turkish university system. So it is ranked as the first national university, public university in many different rankings. Like all the education or all language is in English. Like, let's say we are also lucky that we have many foreigner faculty members. Maybe 20% of our faculty members are foreigners. And we have a very strong computer science department in the university. So this is the standard general introduction for this university, if you don't know. And now these days, our university became a headline in many newspapers because of some recent events that we are at the moment suffering. So our university was or is very strong because of its independence. But these days, like lately, one month ago, the president of the university was directly appointed without our knowledge. So now there is some problems in the university that we need to deal with. We resist actually, but let's see. So we try to keep the quality of the university and improve it. Anyway, so this is if you heard about the news, that's why I put this slide. So this is my group. I started working in the university 5 years ago, like 4 or 5 years ago. Now my group is composed of around 10 graduate students. And so in the group, what we do research in 3 main directions. On the right, you can see I named them like computational modeling, cognitive robotics, and some more industry-related adaptive intelligent manipulation. So to just give some brief idea about what we do, for example, for computational modeling, in this picture you can see that we try to understand how the perception of people change if we change their body parts. Of course, we cannot change their body parts in reality, so we use virtual reality. And then we let people to interact with objects in the virtual reality with change body parts. For example, in one of these studies, we changed the hand with a capsule, so people cannot do grasping anymore. And then we try to understand how perception about graspability or reachability changes using different paradigms from cognitive science. So what we do, there are different other works. So we try to understand about the mechanisms behind these cognitive skills in humans in that research direction. So our university has a master program named Cognitive Science. And in that master program, students are co-supervised by 2 faculty members from one of the 4 departments that includes computer engineering, psychology, linguistics, and philosophy. And based on this interdisciplinary supervision, students try to, or with students, we try to understand different aspects of cognitive capabilities. Okay, that is the first one. The second one is about cognitive robotics, and then I'm going to present the latest work we did on cognitive robotics. And the third one is so learning for intelligent manipulation. So you know that manipulation and tool use are extremely important in industrial settings, and we cannot hand code, pre-code all the skills. So the robots are required to learn, and they need to learn efficiently, which means from minimal data, and they should be able to execute the actions like unscrewing or using other types of tools, assembling objects, disassembling objects in a robust way. So that is the third direction. And all of these projects are supported by different funds like European Union or some national funds, and we have some good connections with Tokyo and Osaka University. Okay, so let me start today's talk. So I think it is important to in order to give a perspective, it's important to have a look to the history. So in robotics, so people in robotics sometimes may not be aware of this kind of stuff. But so the first maybe autonomous robot that was in operation with many different capabilities, or one of the first ones is this one from Stanford University. So this robot is called Shaky because its movements are shaky when it moves, and then that robot is equipped with all the available actuators. Actually, it doesn't have an arm, but otherwise, like it has the mobility. And many different sensors. So this robot is a very important robot because it can make intelligent reasoning and planning in order to achieve different tasks, different given goals. So here you can see it has, for example, range finders for depth perception, or some camera for communication, and some bump detectors and things like that. And it is placed in environments with different objects. So these are some different objects like cubic ones or rectangular ones. And the most basic capability of this robot is to perceive these objects and then reach to a goal position that might be a different room from the current position using the map of the environment. Okay, so if you are interested in this history, I think you can have a look to this paper that was published 3 years ago in 2017, strips any approach to the application of the problems to solving. Sorry, so there are two papers here. The second one is about Shaky, this robot, and its cognitive architecture. So both in low level and high level in 2017. And this first paper was published in 1971. So this paper lays the foundations of the planner that this robot uses. So this planner is called STRIPS. That stands for Stanford Research Institute Problem Solver. So given a goal and action, some operators, this STRIPS planner can be used for problem solving. So these days there are very advanced planners around, but actually, so in my opinion, so this STRIPS planner is a deterministic planner, so it can make plans in the deterministic environments, assuming deterministic action sequences. But otherwise, so all the planners that are built after this follow similar principles, can solve similar problems. So I think it's important to emphasize this. So this is an example from such a plan that the agent needs to solve. So the agent in this case, Shaky, is given the map of the environment, and then there are different rooms, different objects with different properties. So it should be able to detect those objects using its sensors and then make plans. So this is these are the symbols that Shaky used to make plans. So the robot is given a world model which gives information, symbolic information about the world. So this world model includes some predicates like connects. This connects predicate is used to define to describe that room 1 and room 5 are connected to each other through door 1. Or it gives information about the boxes and light switch and all this type of information. So given this kind of world model and in some other plans a complete map of the environment, and then the robot is also given the descriptions of the actions. So they are called symbolic operators, and I just give you 3 of those symbolic operators. They are goto1, goto2, and push2. So these operators define preconditions and effects of actions. So in order to apply, for example, push2 action, these preconditions should hold. And it also describes after a potential push2 action is executed. So it says that the preconditions are M should be pushable and it should be on the floor. M should be next to the robot, and all these predicates should be true in order to apply this action. And after applying this action, some of these predicates are removed from the world model and some others are added to the world model. Okay, and using these operators and starting from an initial world model, the planner tries to find sequence of actions, and in this case, it means the sequence of operators to bring the world model into a desired one, which means that given an initial world model, it finds the sequence of operators that generates a world model with some goal symbols true. Okay, so these are the basics, and these basics actually, like, some details changed. Still, these basics are quite valid for even AI planners. Okay. So we said that the robot is given a model, and in this model there are predicates. So, and we said that the robot, when it is in an environment, it needs to find the correspondence between these predicates and the image coming from its camera, for example. Like, there are different boxes here in different types. Let's say that there are 3 different types: box 1, box 2, and box 3. So it is required to assign each of these detected boxes to one of these types in order to make further reasoning. So then, as you see, there are predefined predicates that are defined, that are represented in symbolic domain, and the robot has incoming information in high dimensional and low resolution and real value domain, like camera images. So now you can now guess what symbol grounding and symbol mapping is. So the robot is required to map the the camera, in this case, the camera images to the corresponding symbols. So I guess you can hear me, right? Lorenzo, you are still there.
Yes, yes, we can hear well. I can hear.
Good. Good. Okay. So what they do, what you can do actually now is, so given these camera images, so this is, let's say this is, we generally call this continuous domain. So because each of these image, for example, is composed of many pixels, where the pixels might take values that are not necessarily discrete. So it is very high dimensional and continuous. And the robot needs to be able to map these symbols into different box types. And for that, what they can do, like in 1970s, they wrote some hand manually coded detectors to map these symbols to the images. And later people, of course, start doing writing some learners that can map the continuous data into the symbols. And this is generally what people do. I mean, these are old images and old symbols, but that is how people see this process. They pre-code, hand code these symbols and the operators beforehand, such that with these symbols and operators, the problems can be solved using planning. And then they train classifiers to map these the incoming sensory information to the corresponding symbols, such that when the robot encounters with a new sensory information, an image, then it can predict which symbol it is, and then it can use that information to make some plans. So this requires predefining all the symbols. You need to define all the symbols on the right and then learn the correspondence between the images on the left to the right. But now the big question is, can we predefine all possible symbols in all tasks? And it is shown that for some limited environments, yes, we can maybe define some symbols, but as the complexity of the environment increases, when we try to scale up to more complex environments with more uncertainties and for different types of robots with different actuation capabilities and sensing capabilities. So this approach, predefining symbols and learning the relation, is found to be not feasible. So why do I? So of course, there is no theoretical proof that it is not feasible. But so to date, after 50 years from shaky times, we still don't have systems that can robustly make plans in realistic environments and use this kind of mapping effectively. So many people, I think that this is not the way to go, predefining all possible symbols and after learning. So what we require is probably the robot with its interactions with the world should somehow try to find out which symbols can be used, discover the symbols, and then use those symbols for planning. So this is a slide that shows some examples from our world. Let's say that we will try to design, hand code all the symbols. So the first question is like, how many symbols do we have? Let's narrow down the question. Let's say that color is somehow useful. How many color symbols do we have? In our language, probably. And this, of course, depends on where you live. Even it is very difficult to predefine all the color symbols. So this is a chart that shows giving color symbols for different colors in different regions. So people who live in the desert have different symbolization for colors, for example, compared to the people who live in Amazons. So it is not even easy to find color symbols for us, and for robots, probably it is not possible as well. Okay, so all these symbols, predefining symbols, depends on agent and agent's capabilities, environment, and the relation between environment and agent and other agents. So it is not probably possible to predefine a general set of symbols. Okay. So then, I already told that. So the other way to go is not to predefine symbols, but to let the system interact with the environment and discover some symbols. But it is not only some symbols. So discovering or finding symbols from continuous data corresponds to some categorization. So we have some continuous high dimensional data, and finding symbols in this data correspond to discretizing that information. But there are millions of ways of discretizing the same information, same continuous data. So it is utmost important to make this discretization with the aim of having or obtaining some useful symbols, the symbols that can be used for reasoning, for planning, for communication, for language. So only if we can find some useful symbols for this purpose, then it would be possible to use these symbols for high-level cognitive capabilities. So this is a very nice image from Justus Pieter from Innsbruck University. So this is kind of this provides the idea. So the robot initially is given a set of objects, and the robot has no idea what those objects correspond to. So if they are pushable, graspable, if they stack on top of each other, things like that. But after all exploration and interaction, it discovers symbols, and using these symbols, it can make plans like something like this. So if you are interested in this symbol formation, symbol discovery, you can have a look to this survey that we wrote together with Lorenzo after a one-week workshop, Symbol Emergence in Cognitive Developmental Systems. And there are some other references if you are interested, I can provide you. Okay, now finally, I will describe in maybe 10 minutes what we did for this purpose. Actually, we did some stuff previously, but this is the latest work where we used some neural networks for symbol generation and rule learning. So previously, in some of these references, like for example, George Kounderis has very influential work. His work, I think it's not here, his paper in 2000. So his latest paper got the best paper award in the main artificial intelligence conference and journal. And we also had some work. And in all these works, what we did was applying some different machine learning algorithms for clustering, for classification and stuff like that. And in all of that, like we were just connecting one machine learning algorithm. We were using one machine learning algorithm to solve one problem and another machine learning algorithm to solve another problem. So these are, of course, I cannot talk about George's work, but at least my previous work was not very principled. So we were just using some algorithms to solve some problems, but we couldn't provide a general framework to solve this. Now, this new work is more general. Let me explain how it works. So let's see, there are 4 steps, and this you can see this as a loop. And I will give the details, and the most important one is the second step. In the first step, it shows the robot, in this case, a simulated robot interacts with different kinds of objects, like it can push objects in different directions, and it can grasp objects and grasp and release objects on top of each other. And from these interactions, the robot sees the objects. It has no idea about the symbolic information, but the robot observes the environment using its camera. There's a top-down camera, and top-down camera gives the depth image of the environment. So depth image before the interaction with the objects, and depth image after interaction with the objects. And in the second stage, using this depth image of the object, so this is continuous information, it finds symbols. I will give the details in the next slide. Using a deep predictive network. So this predictive network takes the initial image of the environment as input, and it uses an encoder and decoder. The output of decoder tries to predict the consequence of the action, and there is a bottleneck layer which has discrete activation, and through this discrete activation it finds the categories. So each of the continuous input given as the image generates discrete activation in the bottleneck layer, and this discrete activation is used as the object symbol. And with this discrete activation and action, the system is supposed to predict the effect of the action. Okay, so in this way, the system finds high-level discrete object categories, object symbols, and effect categories. And the low-level continuous interaction of the robot that it observes through Kinect is now encoded as some symbolic information. This symbolic information is used to train some decision trees. We use decision tree learning because decision trees can represent any sentence in propositional logic. And later, these are automatically translated to strip symbols that I showed in the first slide with Shaky. Okay, so this video shows the first step. The robot interacts with objects using predefined actions. So these predefined actions are like push and grasp and different pushes. And there are different objects, as you can see. Here you can see the interaction experience of the robot. Before push, the robot takes the snapshot of the object, and this is the depth image. And after push, it takes another snapshot of the object. Of course, there are many assumptions and simplifications. Like here we use the snapshots before and after action, but actually a better system should have used the temporal sequence or trajectory observed during action execution. Anyways, so our system takes snapshots before and after executing the action, and each of these actions, this information is stored. So there are 5 different objects like spherical, cubical, vertical cylinder, horizontal cylinder, and cup. And for input, we use directly the image, and for output, which corresponds to effect, we couldn't use this low-level information. We couldn't manage to run the system with this low-level information. So the effect that the system is required to predict is the change in position and force feedback of the robot. So robot has a force torque sensor in its wrist, and the system should be able to predict the change in position of the object and also the change in force feedback. So the previous one was actions that are applied to single objects, push front, push left, and push top actions. And there's another action which can be called stack. In this case, the one object is released on top of the other object. And here you can see the initial snapshot, and you can see the final snapshot after this interaction. So this is the interaction experience that is collected by the robot. And here you can see there is no symbol. All this information is encoded in continuous world. And this video shows some examples from stack interactions. Okay, so this is the interaction and learning experience of the robot. So in the symbol formation stage, this neural network is used to find the symbols. So let me give the details. So the input of this network for push actions is as I told you, the depth image. And there is an encoder layer. And this with this encoder layer in the bottleneck, there are two neurons that have binary activations. And there are some, so the actions are encoded binary as well. There are 3 actions. So therefore, for each of these actions, one of these bits are activated for the corresponding action. And at the end, after encoder and after a decoder, the system is supposed to predict the consequence of the action on the object and force feedback. Here, as you can see, what we do is we force the system to discover some categories, some object categories that are useful, or we can call object symbols that are useful for effect prediction. And maybe some of you might have some question because this is based on error backpropagation, as you can guess. And so there is a nonlinear unit here, so binary unit. So in order to backpropagate the error from the output all the way back, there is a trick called straight-through estimator, where the backpropagated error is directly sent to the earlier previous layers without any change. So that is a hack. So there is no gradient taking here. That is a hack that works well practically. So if you are interested in this, then you can search straight-through estimator. Okay. So the object symbols that were discovered are shown here. As I told you, so there are 2 units here. Therefore, with this architecture, the system can learn 4 different object symbols, object symbol categories for activation of 0, 0, 0, 1, 1, 0, 1, 1. And when we check out how these activations are generated based on input, so this is the result. For example, the activation 0, 0, let's call this 0th symbol, are created by these images. These images correspond to rollable cylinders. The rollable cylinder can roll in one direction. 0, 1 is generated by these images that correspond to spheres. Spheres can roll in 2 different directions. 1, 0 is created by these images. These images correspond to boxes or upright cylinders. So they share the characteristic that they can be pushed in different directions with similar amounts. And the final symbol that was found was generated from these images, which are kind of cups that have some openings at the top. So we can call them insertable objects. As you see, now the system was able to generate symbols 0, 0, 1, 1, 0, 1, 1. These are symbols that the system generated using these images. So Lorenzo, I have 5 minutes left, right?
Yeah, please.
Okay, so I also wanted to make sure that we are still connected.
Yeah.
Okay, so these labels, rollable, unstable, stable, insertable, we can give any label, and actually the system does not need any label. So the system finds the symbols, and we don't need to actually give labels. So I think labels become very important when we try to communicate these symbols, like in humans. So we use symbols, like gestures or symbols in the language for communication. But for planning or reasoning, we don't actually need these labels, but the system can directly use the corresponding discrete encodings. Okay. So this shows how the actual objects that were used in the experiments were mapped to the symbols that are found by the system. Here, as you can see, cube and vertical cylinder were mapped to the same symbol 1, 0 because they respond to robot actions in the same way. The robot actions are push left, right, and push top, and then the vertical cylinder responds same. That's why this method categorized these objects in same symbol. So if you have questions, a lot of time I get questions instead of this, what happens if we use autoencoders? Then I can show the results. What happens if we use autoencoders? But let me continue. So these were the symbols from single object interactions. And we would like to use these symbols like 0, 0, 0, 1, 1, 0, whatever, for further learning, of symbols, more complex symbols, for example, symbols that appear in stacking. For that, what we do is, for stacking, so okay, we freeze this network that generates the symbolic information given a single object image. And then we use that network in order to learn paired object interaction and symbols. So what happens is, okay, let me show. So in this case, the system tries to learn symbols for stacking. And in stacking, there are 2 objects, of course, object 1 and object 2. The system directly uses the categories. For example, this symbol had category 0, 1, I think, and the second object had category 1, 1, along with a new encoder that is supposed to find some relational symbols. So if we use the language, then this complete network is supposed to predict what happens with stack action given rollable object and insertable object and some new relational symbol that is required to be discovered. So therefore, the encoder that comes from the first interactions are frozen, and new relational or paired object encoders and decoders are trained. And here it's supposed to find a category that is useful for predicting the effect. And in short, the system finds a symbol that represents the relative size of the objects. So, and we can call that symbol as is larger than, because so given different objects, for example, an insertable objects in the bottom and then another objects at the top, when the robot releases the object or inside an insertable object, depending on their relative size, different effects are observed. And this relational symbol, which we can call is larger than, encodes that kind of information. Okay, I'm almost done. So these parts are not, I mean, they are not that interesting, but we need to close the loop because now we have symbols. Now we need to learn some rules from those symbols. And for rule learning, we use decision trees from the interactions. And from the decision trees, so these strips-like operators for each action, which encodes the predicates as preconditions, and effects for preconditions are extracted. And so now, because like these days, uncertainty is very important, not these days, but in general, uncertainty is very important. We try to find some probabilistic rules. So for example, in this case, in this example, this probabilistic rule says that what the system learned, so there are two objects below and above, and below object is type object 3. It is 1, 0, and above object is object type 1, which is 0, 1. And the relation is relation 1. It is larger than or smaller than. So if this is the precondition, and if the robot applies stack action, then there might be two different effects. So with 0.57 probability, this effect happens, and with 0.422 probability, another effect might happen. And now this is called PPDDL, probabilistic PDDL operations, problem domain and definition language operator. We can give these rules that are discovered by the robot directly to AI planners to make plans. Okay. So we don't have time. If you have any question about this decision tree learning and how we convert it to PPDDL operator, I have slides I can explain. But maybe you get a bit bored, so I will show some videos. Now, after all these learning, symbolic and rule knowledge, now we can ask the robot to make plans. In this case, we ask the robot to make, given these objects, we ask the robot to make a plan, create a tower whose height is 1, so small height, using 4 different objects. And because the robot learned about the symbols of the objects, in this case, like insertability, not insertability, and things like that, and relational symbols, the generated and executed plan is like this. So if we ask the robot to create a tower of height 4 using the same set of objects, then the generated plan is as shown. Yeah, so the robot, based from its interactions, it learns some meaningful symbols and rules that include different properties and relational properties between objects. So if the object is insertable and the object being released is smaller, then it will be inserted. Otherwise, it will be stacked, having a high tower. So this is another objective: create a tower with 5 objects. And as you see, again, so this is a very meaningful plan. And as you see, this object, rollable object, is placed at the end, because if it was placed, the sequence was a different one, because the robot learned that it cannot stack the objects on top of spherical objects. Spherical object, as you remember, had a symbol 0, 1. So the robot learned about the, let's call, object affordances, what objects afford to the robot and to each other. So there are many different example plans. I am not going to give details. So this is the conclusion. But before giving the conclusion, so I'd like to emphasize that, so in this work, what we did was we mainly proposed a deep neural network with this discrete activation, bottleneck activation, that learns object, action, and effect related categories that can be used for planning. And we believe that this is quite a generic and principled way to do this. So we have high hopes. So we will try to scale up. But before that, because of the pandemic, we couldn't make real robot experiments. So this is a robot experiment from a previous work that didn't use this kind of deep neural network. But if we used a real robot, then probably we would have seen something like this. So here I asked the robot to create a tower. Then, as you see, it starts from larger objects because they would probably generate desired effects. Okay, so this work was done in 2015 in Innsbruck. So hopefully after we can again start going to the lab, we will transfer what is learned in the simulator that I showed previously in the real robot. And I think the most important question is, I think the system works quite well for limited set of actions and objects. But when we try to scale up, things get complicated greatly. Like when the system executes the plans to create towers, then it will start observing some object compounds that were not observed before. For example, this one. So this one, is it insertable? Is it stackable? Or this one, the last one, is it insertable? Is it stackable? So there are, we need to make, we will need more complex representations and ways to encode this. For example, insertability of this object. So it depends on the object to insert. So you can insert four board markers, but you cannot insert 10 board markers, for example. And our system cannot make this kind of reasonings. So it should be always in the learning loop. So the story that I have told today learned like this. There was step 1, interaction, step 2, symbol formation, step 3, probabilistic rules, and step 4, symbolic operators. But with these symbolic operators, there will be some plans, and using these plans, the robot will come up with or encounter new objects, and they should also, the robot should also continue learning those objects. So this should be designed as an actual loop, and it is not that straightforward to actually scale up. For example, in this case, there are two objects for two object interactions, and we can have a network like this. But if there are n objects, how can you deal with n objects? Then things get complicated. So for n objects, we have some idea. So for example, we can use graph neural networks to encode n objects. Let's say we would like to find a symbol for this kind of situation. This situation can be encoded as a graph neural network, which is quite popular these days. Each node corresponds to a single object category symbol, and there are some relations in between them, and the system learns a symbol for each graph. So but in general, this is a difficult problem. Okay, so this is the main work is by my PhD student Alper, and these are my collaborators. So thank you for listening. So if you have any questions, maybe we don't have much time left, but
yeah, thank you very much, Emre. That was very it was very interesting, and thanks for the detailed explanation. I think it was interesting for everyone. It's nice to have sometimes, as you said in the beginning, like you could have given a more general talk about several things, but I think sometimes it's very nice to see details of one specific work. I think it was very informative, and for everyone, and especially for the students of the cognitive robotics module, surely they saw some connections between what you presented and what you have seen in lectures, for example, of this kind of duality between what I have called the cognitivist approaches and emergent approaches, right? So those approaches in which you define a set of rules and then the system, the robot will reason upon them, or those approaches in which you try to understand this symbol by interacting with the environment. So I think it was brilliant.
So just as a side note, so there is a new emerging field, maybe you have heard, neurosymbolic AI. I think it will become more and more popular soon. For example, this year in AAAI, there was a special track for this neurosymbolic AI. So people who are interested in combining these ideas might have a look with that name.
Okay, neurosymbolic AI. Okay, I see. Yeah, good to know. Thanks. Okay, so if anybody will have questions, the hour is finished, but if Emre is available, we can stay definitely a few more minutes. So there was during the talk, I saw there was a question from one student about the way in which you take these snapshots of images. So the question was, let's say, how long do you wait? But in general, I think the question can be, yes, if that was a fixed amount or if that created problems, like how would you deal with that simplification? I mean, of course, you said there are a few simplifications in the setup, which is always the case when we do these experiments. But yeah, if you could give some details about that.
So yes, I think, thanks for the question. I think that is one of the most important things we hand design. So let's say that the robot executes a role action. It is easy to get the first snapshot because so the environment is stable and not moving, and we take the first snapshot and we say that okay, that's supposed to create the symbol for the initial world state. But let's consider about push action, and the robot pushes a cylinder or sphere. So then we would like to encode, we would like to represent the outcome or effect, and we would like to take a snapshot. At which point are we going to take the snapshot? So when one option is when the object becomes stable again, so everything becomes stable again. In that case, maybe the spheres and cylinders are out of the scene and bugs or other objects are inside the scene. So that might be one option, but so when we have more complex actions and moving environment, more dynamic environment, I think the answer to this question becomes more difficult. And I think maybe so. I think we are taking these steps, very small steps. So we are in much better position in terms of generality of these solutions compared to like 10 years or 5 years ago. But maybe within 5 or 10 years, we should be dealing with continuously changing effects. So instead of taking a snapshot and representing as the output, what we probably need to do is we should form the symbols or learn from the continuous interaction that, in that case, that corresponds to trajectory of force torque sensor, for example, or the video, the complete video of the interaction. So that would be probably one of the next challenges.
Yeah. So you mentioned also in your talk that, of course, having maybe the complete video would be like even more interesting representation. Do you think that will be feasible computationally, let's say with similar architecture to what you have, or it needs to be something radically different?
So I don't have a definite answer for that, but we will start working on that because of two reasons. First, it is important to be able to encode this continuous interaction. Second, there are data sets. So in our work and in some of your work, you know that we need to create our own data sets ourselves. And it has, we need to spend a lot of effort first. And second, so we do our experiments with our data set, others with their own data set. But there are some data sets from robots or from humans. There are many data sets from humans, interaction data sets. And I think it is very valuable if we work on these data sets and try to find some symbols on these data sets. So I think the main message or the main component that is exciting for me is that binary activation layer. So maybe that is the core, and I think I will pursue trying to use that binary activation layer because it directly gives some discrete information, some symbols. But in order to deal with that continuous videos, then probably we need to use more advanced deep learning architectures techniques.
Yeah. And I mean, and you touched upon data sets, which of course it's good to see that now in general the robotics community have started to have more and more of this data set and more usable ones. So yeah, that's definitely important. Well, I don't see it. Okay, so there is another question. You had pre-chosen actions. Do you have plans to expand this range or allow the system to learn new actions that will increase the distinction between the symbols? So I think maybe what the question is aiming at is, of course, the possibility to add additional actions, but maybe even more crucially, to add actions that will help to increase the distinction between the symbols. So like specific action that would maximize the number of symbols you can discover, basically. I'm not sure if that was the angle, but it can be maybe an angle I'm giving you.
I think that that's a great point, and probably that is the most important limitation of our system, or most important assumption that we made. We assumed that there are discrete actions, and that really simplified the process of finding these object symbols. Because what I say is, so we would like to have a method that finds symbols from continuous interaction. But as the audience noticed, it is not completely what we observe is not completely continuous. So we have discrete actions that we assume. I think so. In general, how I I think it is very important to discover actions. And if we had a system that can completely deal with discovering both action symbols and object symbols, effect symbols, this would have been great. So if we have a look to, for example, biological development, then what we notice is, so the human infants, for example, they first up to 9 months or 12 months, they first develop some action repertoire, like grasping, like pulling, maybe shaking. And after, of course, it is not strictly sequential, but there we can notice a sequence. And after finding those discrete actions, then they start learning about the causality for those actions. And more complex actions are generally learned from others through parental scaffolding or from imitation. So what I would like to do is I would like to keep that simplification there because so we actually don't have many action primitives as well. Like, so in my opinion, there is just pushing and pulling is another version of pushing. There is grasping, there is releasing. For example, throwing corresponds to releasing with a high velocity. So I believe that there are not that many action parameters, action primitives, but of course those primitives might be parameterized. But I would like, this problem is a very complicated problem, so I would like to kind of get inspired from development, human development, and then let the system first discover actions, and then you use those actions to discover further symbols. And we did some work on this. We and some others also did some work on discovering actions. There's a big literature, of course, in self-discovering actions and discovering actions based on some reward. So, for example, in reinforcement learning, the agents discover actions that can be represented as options, or through exploration using some clustering based on some force feedback, the system can discover some action. So that's a difficult question to answer. I think we need to make some brainstorming instead of trying to answer that question.
Yeah. So the other, let's say, question or part of the question would be, even if you have, let's say, a limited set of actions, such as the ones that you have in your system, in your implementation now, on whether the selection of those actions in the exploration phase, it's I mean, of course, it could be, let's say, random, which is also something that even people in developmental psychology, sometimes they talk about this random motor bubbling. So the fact that some of the actions are more or less random, or motivated by external environment, like you want to do something and that's the action you do, or also motivated by internal drives, right? And those internal drives might be those that will make you select a certain action because that's the best action in order to discover a new symbol.
Exactly.
Yeah. So I don't know if, I think that's.
Yeah, exactly.
But yeah, you mentioned reinforcement learning, which could be, which is indeed the framework that can put those things in, right? In terms of selecting the action that will either follow an internal drive and maximize that, or achieve some other thing.
Yes. So exactly. Yeah. I mean, so if we have a look to these biological systems, really, like let's say that cup stacking for an infant. So why should an infant learn an action for stacking cups, right? And there are many different ways to explain that. And it is a combination. So because it creates an interesting outcome when it's stacked. And also sometimes parents step in and then show the relevant cues to drive the infant, or directly show the action. So there are different ways. And probably it is combination of these intrinsic motivation type of approaches combined with reinforcement learning.
Yeah. Yeah, I mean, maybe one last short comment that I liked in your presentation, that what you showed, that basically you learn some symbols in the first part of the exploration that you showed, and then some of those symbols you can reuse to learn something additional, which I think there you see the, let's say, the power of symbols. Because otherwise you may say, okay, maybe we don't need these symbols at all, right? You can learn end-to-end, like whatever sequence, and the robot will learn how to do certain action and see the effects. I think the power of what you showed is that those intermediate layers in which you have the discrete symbols, then they allow powerful generalization to learn something new. So the second task that you presented of the was that the insert,
Stacking,
yeah, stacking, yeah. So if you will learn that from scratch, right, that will take much longer. And
exactly. So about that comment, I have a very short comment. So I believe that this learning of symbols is important, but what is more important is learning abstractions and then transferring that kind of abstraction. So we learn discrete symbols because that they can directly be used for in AI plan. But if somebody says that I would like to learn continuous abstractions, that is as valuable as well. I mean, so what is important is abstractions and reusing those abstractions for learning more complex capabilities.
Yeah. Okay, there is a question: is that symbol learning process robust to noise of the environment or a stochastic environment? And yeah, that's the question.
So,
maybe a bit related to that, I will add that you showed in the end that then you can use those symbols in a probabilistic planner. So I'm not sure whether this is related, yes. Which in this case I will ask also if you can specify how do you actually get those probabilities in your system. But the actual question was, yeah, whether the symbol learning process is robust to noise.
So actually, we didn't make a systematical analysis on how robust it is, but as you said, we created, we used probabilistic rules and later probabilistic planning operators in order to encode the uncertainty. And actually, when we check out those probabilities, we see that those probabilities can really encode that uncertainty. For example, so what might be the uncertainty? When the small box object is stacked on top of a big box object, then a stack is formed with high probability. But if a big box is stacked on top of a small box, but then now there's some probabilities of stacking or tumbling. And it is represented in that probabilistic formalization. And when we give these probabilistic rules to these planners, probabilistic planners, they can actually make use of those probabilities. But we didn't actually make, we didn't analyze how robust it is by increasing the noise level. Maybe that is what we should do next.
Mm-hmm. Okay. Right. If there is no further questions, I think yeah, this is enough for today. I think it was great. I mean, I will have other questions to ask, but I think as soon as possible, Emre, we should have maybe another chat because yeah, there's I think there could be things that we would like to discuss. Yeah, the presentation was great, and thank you so much.
Thank you for the questions. They were all perfect questions. So people actually listen to the talk, I can see.
All right. So with this, we close this this seminar, and I will now stop recording. As I said, as soon as possible, I will put these all these seminars live, available, and public for everyone. and you will be able to monitor this on the web page in which all the seminars are listed. Yeah, thanks again, Emre, and
Thank
hopefully
you.
soon.
Yeah, it was very nice to see you. Thanks. Bye then.